All right, here we go. Let's go. Come on. Notes out. Okay, so we practiced yesterday. Yeah, go ahead. You bet. We practiced our inductive thinking a little bit. We looked for patterns. We found some patterns. We found actually a pretty good pattern. Yes. Okay, we found this pattern, right? We found the pattern that if I take, right, turn around. If I take the pattern a plus b to the n and I expand it out, I mean, who knows, the number of terms depends on how big n is. But we saw a pattern developing, right? And we looked at the first 1, 2, 3, 4, 5 terms in that pattern, which is pretty good. What we ended up with was, really, this is the same thing, by the way, as saying we got a to the n over 0 factorial. 0 factorial is defined as 1, just like 1 factorial is. So we just gradually worked our way up from 0 to 1 factorial to 2 factorial to 3 factorial to 4 factorial, being the constant in the denominator. And then, of course, we had the pattern a is going to start off with all of the exponential weight, b has 0. Each term ratchets b up by 1 and a down by 1, right? And the numerator of the coefficient ended up following this bizarre pattern. So we had n times n minus 1, n times n minus 1 times n minus 2, etc., etc. So we get this product that keeps with an additional factor for each term that we step in, right? And so, we had a pattern here. That's enough, right? We essentially almost found the binomial theorem, really close. But we got the first 5 terms of the binomial expansion.
Really
so
fast. Are you recording?
I am. Thank you. I am. So now we get to do a trick, right? So now what we're going to try to do is we're going to try to come up with this, right? We're going to try to come up with a trick that's going to allow us to differentiate a power function, x to any exponent, and come up with an immediate answer rather than having to go through this enormous limit process for our derivatives, right? So what we need to really do here is we need to go from this step right here down to this step right here by using, well, that, right?
Yeah.
So maybe what we need to do here, what might be useful, would be for us to, let me rewrite this more neatly, and then I'll cut and paste it onto the next page so we can kind of stare at that while we use it, right? Okay. So we ended up with our pattern being a plus b to the n was equal to a to the n plus, we'll just make these numbers on the bottom, how about, right? That's fine. Plus n a to the n minus 1 times b over 1 plus n times n minus 1 a to the n minus 2 times b to the 2 over 2.
Oh, it's all over 2?
Yeah, all over 2.
Everything.
Okay, I mean, same thing as all being over 2 or just the front being over 2. Doesn't matter,
Oh,
right?
okay.
Okay. We'll just do the first 3, how about? Knowing that we're gonna keep seeing this pattern over and over. Plus n times n minus 1 times n minus 2 a to the
n minus 3 times b to the 3rd all over 6.
Okay, good enough. All right, so let me copy that.
Hey, now.
Game on.
Okay. All right, back up here, please. So there's our expansion. Now instead of A's and B's, what we've got here is an x plus delta x to the n, right? Okay, so I'm gonna have to write a little bit smaller, but we're gonna expand this using our new trick, right? Our expansion that we discovered, our pattern. So what's that gonna be? So this is gonna become, okay, so instead of a to the n, we're getting x to the n, right?
Yeah.
So we get x to the n plus, okay, n times, instead of an a, we've got an x to the n minus 1 times a delta x to the 1, right? Plus, this is going to be an n times n minus 1 over 2, we'll just write it as a fraction, times a to the n, not a, x, x to the n minus 2 delta x squared, right? Maybe there's even room for one more. Plus, if we continued, we would have gotten n times n minus 1 times n minus 2 over 6. Yeah.
For that n times n minus 1 times n minus 2 over 6, did you just change that to could you just do, never mind. Let me think a little bit.
Could I expand it out?
No, let me think. He's trying to compress it.
Oh, no, you can't compress it.
No, just let me think about it.
Because it's already factored. Right, it's already all factored out. There's really, let me preemptively kind of answer your question. What we're going to find is it's not going to matter. Okay, pretty soon we're going to see that it's not even going to matter what that looks like. So you'll see in a second. Okay, times, what are going to be the powers of x and delta x here?
N
To the n minus 3 delta x cubed, right?
Yeah.
Plus, etc. On and on and on, right?
Yeah.
Okay, so we got all that stuff minus, okay, it's a little, just, I need outer tension here, minus x to the n, right? Because that's, right? So here was all the red stuff, minus, I guess that minus should be neutral, that's going to be black, but then we had the green, f of x was x to the n, right?
Yeah.
Think what we're doing. We're just plugging this into our generic pattern, f of x plus delta x minus f of x. But in our case, f of x was x to the n, right? Okay, questions? Okay, in the denominator, we just had a delta x, right? And we're taking the limit as delta x goes to 0. Good. Okay, so that looks like a mess. Looks like a total mess. Well, how are we going to do anything with that? Okay, is there something we can do? Well, is there any cancellation? Ah, okay. So even though we skipped some unknown number of terms here, we can still see that when all the dust settles, because really all that's happening here is the powers of x are decreasing and the powers of delta x are increasing with each term, right? Okay. We can see that eventually this term and this term are going to cancel. So all we're left with is this stuff right here. What's my next step? Okay, yeah. Now look, all of these terms contain a common factor of delta x, right? Delta x and then increasing powers of delta x as we move to the right. But I could factor out a delta x to the 1. Okay, so what happens if I do that? I get the limit of delta x times a bunch of stuff. What's left up here when I factor out a delta x from each of those terms? What is this term going to give me?
Nx to the n minus 1
Okay, this one's going to give me
plus n times n minus 1 over 2
times plus
n times n minus 1 times n minus 2 divided by 6 x n minus 3
delta x cubed
squared.
plus or squared. Yeah. Whoops. Okay. Oh, did I mess that up?
Yeah.
Did I forget one?
You're supposed to take
Oh, that's supposed to be squared. This should be cubed. Oh, you're right. You're right. I forgot what we were doing.
Me too.
There we go. Right. All over. All over.
Let's factor it. Well, this is not even include those. You can cancel. How about we factor in n?
Okay, so now what goes on? I factored out a delta x.
It cancels.
Okay, good. How many factors are there in the numerator there?
A lot.
Well, there are now two, right? I've got delta x times that big factor, right? Okay, I can cancel out
The delta x.
the delta x's, which removes the indeterminacy. Exactly. So now I can directly evaluate. Okay. Say it again.
You're just gonna get left with that nx.
Exactly. Okay, so look what happens. Okay, so you're seeing it. When I evaluate this at delta x goes to 0, each of these terms contains a factor of delta x, right? So all of those are going to go to 0 all the way down the line, and the only surviving term is that first one that had, right? So that's our answer. We got it. Okay, so we got the answer back.
So what was the point of that?
This is the point. Now, this is the good stuff. The derivative of a power function of x to the n is always equal to nx to the n minus 1. Okay? 2 days of worth of stuff for that. But now it pays off. Now watch. We can do, hang on, I'm gonna go back. There we go.
Is that d over d of x?
Yeah, that just means the derivative. Remember, that's our notation, our weird notation for just the derivative of that function.
So when we're finding the derivative of anything, we just do nx n minus 1. So at least we know how we got
Yes. Yes. So now let's put this to practice. Now look at all the time this is going to save us. So are we ready? Can I turn the page?
No, this time we're going to be x, like x to the power.
Yeah.
It only works with x to the power.
Yes.
It works with anything.
Well, any situation that can be written in this form. So we'll see. It's pretty tricky. We can do lots of stuff with it. Okay, here we go. So try this. Let's say f of x is x to the 17. What is f prime of x?
17x to 16.
17x to the 16. That's it. So you see the pattern. The exponent is multiplied by the coefficient, and the new exponent drops by 1. Right? That's it. Okay. Now we can even go further with this though. If we go back, I don't want to go through the whole proof unless you really are just dying to do this. What if, now you got to pay attention though, or maybe I'll have to. Oh, that was a good threat. So what if I had a constant here? What if I had multiplied the whole thing by a constant? Then wouldn't I have just had, when I calculated, or when I evaluated my specific function at x plus delta x and at x, wouldn't I have just had c's there? Right? What I'm saying is, if the original function had been c times x to the n, then f of x plus delta x would have been c times the quantity x plus delta x to the n, right? Now, I could have just, from this point right here, I could have factored out that constant, couldn't I? And just pulled that out in front of the limit, right? Like we did earlier, right? If we have a constant in there, we can always factor constants out of the limits and put them outside, right? So what would have happened then is it would have just been stuck outside until we got down to the very end, and it would have just ended up being right there, right? Okay, so we even expanded our, just with one little tiny addition there, we made this much more powerful. Is now that allows us to do problems like this. What if I have f of x equals, let's say, 2x to the 4th over 3 minus x to the negative 2.
Yeah.
We jumped quite a bit forward, but you can do this.
I do 4 times 22x.
Yeah, just follow the rules, right?
Whoa.
So we've got a coefficient here of 2/3, right?
Yeah.
Everybody sees that, right?
Yeah.
Okay, so I've got the coefficient of 2/3. I'm going to pull the 4 out in front, and I'm just going to get 4 times 2/3 is 8/3. X to what power?
Third.
The third. Now what about here?
Plus x. Here's how we got
Pass that back, please. Pass that to yourself.
Okay. I'm sure, is that like when you are doing anything, you can put the first x one out, right?
Where's Junie?
I have a
Minus x.
Oh, right there, right in front of you. Pass that back. Pass that back. Okay, back to business. Hang on. Shh. Here we go. Riley, up here. Riley, what's the answer to this? What am I going to do here?
Plus 2x.
I don't.
Okay, so this is the, now you're getting wigged out because it's a minus, it's a negative number. No big deal. This pattern holds for any number. It doesn't have to be a whole number. It could be any integer, and it could even be a fraction. So the rule just tells me I've got to take this negative 2 and multiply that by the coefficient. So what do I get? Plus 2. And then x to what? The negative 3. Negative 2 minus 1 is negative 3, right?
I'm confused what you did with the 8x and now it's.
Okay, sure. So how did I get from here to here? All I did was I took the 4 out in front and I said 4 times the 2/3 that was already there times x to the 4 minus 1 is x to the 3. Okay, and then 4 over 1 times 2 over 3 is just 8/3. Right? Okay, so if we wanted to write this in terms of only positive exponents, Hunter, how would I write this right here?
Positive exponents?
Yeah.
Doesn't it go to the denominator? Right?
Yeah, good. So it'd just be plus 2 over x cubed, right?
Yeah.
Right? Okay, more practice. Okay, yeah.
I'm sorry, why did you change that? Why is it a plus 2x?
Because what's the coefficient of this term right now? Negative 1, right?
Yeah.
I got to multiply the negative 2 times the negative 1.
You leave this big.
Yeah. Okay? Another one.
No, wait.
Try this.
I'm not sure if I'm
No, you can. It's fine. But sometimes, you mean in your answer?
Yeah.
Sometimes I'll specifically ask for written in terms of positive exponents. Yeah. Okay, so now what you have to do here to this one, I'm not going to tell you, and I want you guys to work this on your own, please, for a second. You're going to have to do what I like to call pre-write the problem to make it look like a form that's going to work with our new rule, right? This one looks a little funky right now, right? It doesn't look like cx to the n, does it? But so I need to rewrite it in a way that makes it look like some constant. Maybe the constant's 1 sometimes. In this case, it's not. Some constant times x to a power.
Would be 2x to the negative 3?
Yeah, exactly. Okay. So we got to rewrite this. Before we do the problem, we've got to rewrite it as 3x to the 7th plus 2x to the negative 3. Now, I can just apply my rule. So what am I going to get?
What do you want to
Wait, how do you do it?
Okay, question? So it's, okay, so here's the n, right? We're just gonna, now notice also that when we're differentiating these, I kind of slipped this one in there too without really talking about it, but when we differentiate a sum of terms, just like we did with limits, we're able to just think of the process one term at a time. So the way we would say that in math is we'd say we're gonna differentiate term by term. We're gonna differentiate this term plus differentiate that term, right? That's it. That's a huge advantage in the process of differentiating, is that if we have a whole string of terms like in a polynomial, we can just differentiate them one at a time. So really the rule that I kind of skipped over there is a pretty obvious and intuitive one. It just says this: if the derivative with respect to x of, let's say, the function f plus the function g is just f prime of x plus g prime of x, right? I should probably have x's there, right? So I'm just differentiating term by term. Makes it simple. Okay. Unfortunately, I can't do that with a product, and we're not going to deal with that today. But when I get to something like, for example, if this were a factor and that were a factor, well, then that doesn't apply. Then I've got to go to a different strategy. Okay. But we're not there. We're just adding stuff for now. So what's my answer going to be? The first term is going to give me what? Okay. Second one is going to give me 4. And I could put the x to the 4th on the bottom if I wanted to, right? Okay. Okay, now another one. What is, so let's say y equals the square root of x. There's another way of writing the derivative, y prime. Y prime equals what? Now don't say it out loud. Try it on your own, and then I'm going to call it to help us out. Okay, what do you think here? Mr. Bannister, how am I going to pre-write this, do you think, to make it look like something that I can apply that rule to?
Would you take and like use the fraction instead of the...
Okay, so I rewrite this as x to the power of 1/2. Yeah, and now we're set, right? Now that looks like x to the n. So now I just follow the rules. So Janelle, what do I get if I apply my power rule to this?
1/2 x to the negative.
Good. And so if I want to write that in terms of maybe a radical, what's that look like then? So I've got 1 over 2 on the bottom. What do I do with this x to the minus 1/2? Okay, good. So the negative puts it on the bottom, and then an x to the 1/2 written as a radical would be what? Square root. Okay, so I'd write it as 1 over 2 times the square root of x if I were writing it in terms of a radical. Just, I'm not saying you have to, but what if you were, right? Okay? Okay, make sense? All right. Okay, we got that one. That's it. That's how you use that one. It's not a big deal. Okay, what is... No, never mind. Okay. So now, next step. Next one we want to look at, we're going to add another trick, so we don't have to keep doing this limit stuff. We're going to gradually just add a bunch of these new rules that allow us to take derivatives easily, right, without having to do the limit stuff. So the next one we want to look at is this. What if we define f of x as being sine x? Okay. So now let's see if we can prove that. Now this one won't be as bad. It's not as big a deal. So what's f prime of x then? Well, what's our starting place? Limit of f of, well, okay, you're right, f of x plus delta x minus f of x over delta x, as delta x goes to 0. Okay, so then what is the, if f of x is sine of x, what's f of x plus delta x?
Sine of limit of sine to the x plus delta.
Okay, sine of x plus delta x minus, okay, over delta x as delta x goes to 0. Okay, now this goes back to little trig stuff. Do you remember what the expansion is for the sine of a sum of angles?
Nope.
Okay, goes like this. So see if you can fill in the blanks here. If I have the sine of, should I do this with x's and delta? Why not? We'll do it with x and delta x. So sine of x plus delta x is going to give us back. Yeah, it is. It's like sine of a. Let's do it in terms of a plus b, because that's probably what you know. Which it might ring a bell.
Oh my god, it rings a bell.
Oh, it might. Just might. So if we do the sine of the sum of the angles a plus b, that gives us, I'll get you started, sine a cosine b. Okay.
Cosine A of sine B.
Okay, you want to know how, and then what's the cosine one? Do you remember the cosine one while we're at it? It's cosine, I think it's cosine A, cosine B, minus, right?
No, it depends on whatever that plus. Yeah. Oh,
Okay.
yeah. Closer.
You want to know how I remember that? Here's how I always remember that one. I don't remember that fact, but we know what the double angle formula is, right? Those you do know. You know that you should remember those. The sine of 2x is equal to 2 sine x cosine x, right? Remember that one? Okay. And you know that the cosine, well, we're a little rusty. I might have you memorize these again and maybe do a little quiz. Cosine of 2x is cosine squared x minus sine squared x, right?
Yeah.
Okay. So then, doesn't that now, that's the only way we could get those answers. If a and b were both x, do you see that the top one would just give us sine x cosine x plus sine x cosine x? 2 sine x cosine x, right? Make sense? The bottom one would give us cosine x times cosine x, which is cosine squared x, minus sine x. See, that's how I remember it. That's how I remember the patterns. I know these. I can always remember those, but these I sometimes forget. And I just always have to think in terms of these, right? Okay, but we got the pattern. So let's go back and finish this problem up then. So this is going to become the limit of sine x cosine delta x, right? Plus cosine x sine delta x minus sine x all over delta x. Okay, so now what?
Just a second.
Okay, go away. There you go. Go home.
No, wait.
Minus what?
Take out delta x. No, we can't. Take out.
Cancel the sign.
Okay, now, can I evaluate this directly? And the answer is no, I can't, because look what happens. And I shouldn't be able to, should I?
No.
If I try to evaluate this directly, I'm getting sine x times the cosine of 0, which is 1, plus cosine x times the sine of 0, which is 0, right? And so I get sine x minus sine x over delta x, right? So 0 over 0, no good. Okay, but we do have some trig identities, or some trig limits that we want to remember, right? We remember that the limit of, okay, sine x or sine theta over theta as theta goes to 0 is 1. And the limit of 1 minus cosine theta over theta as theta goes to 0 is 0. Okay, so that's big. Can we rearrange these terms in a way where we get something like that? Okay, so what do you think? Okay, say it again.
I was just thinking because like the sine x and cosine delta x multiplied by x.
Okay, so we might have to do some stuff like that. Let me see if I can give you one little hint here. How about if we, I don't want to give too much away here.
Oh, don't worry.
No, I don't want to do that.
Could you take out a sign?
You can't take out a sign because that's a sine of x and that's a sine of delta x and that's a sine of x. But I could combine a couple terms, couldn't I? This term right here has a sine x and that term does, right? So what if we push those together?
Sine x squared.
So let's write this maybe as two separate parts. So I've got the limit of let's take this term and that term and combine them. So I'm going to get sine x cosine delta x minus sine x over delta x, right? Plus, the leftover term was that one, right? So I've got plus cosine x, whoops, I always keep doing that, sine delta x over delta x, right?
Yes.
All in the limit as delta x goes to 0. Can we, if we split those apart, can we do this one? Well, we can, can't we?
Yes.
Because now look at this, we're taking a limit as delta x goes to 0. So what is the, now listen to this very carefully, what is the limit of, what is the variable of our limit here?
Delta.
It's delta x, it's not x, right? Because delta x is the thing that's changing, right?
Yep.
So the cosine x is going to be unaffected by whatever delta x does. Agreed? So I could take this second limit here and I could write this as, I could break this into two separate limits. And I could write this one as cosine x times the limit of sine delta x over delta x as delta x goes to 0. So there's this limit. The first limit, if we split it apart into separate limits, well, before we do that, I'm done with that one, aren't I?
Yeah,
Because what's the answer to that limit? 1, yeah. So if that goes to 1, then this one is done. This term becomes cosine x, right? What about over here? Let's look at this one. We've got this other limit. Whoops, I read. The limit of, if I could factor sine x out, couldn't I? So I get the limit of sine x times, which I could pull out in front of the limit if I want to, there's no delta x's in it, times cosine delta x minus 1 over delta x, right? As delta x goes to 0, agreed? Okay.
But where's the y? Oh, I.
Okay, now that looks familiar though, right? If we look up here, isn't that really the same thing as this?
0. No.
I mean, it's not, but it is to within a factor of -1, right? If I factored out a -1 from this, then I'm just going to get a negative sine x. Let's pull that out front. Times the limit of 1 minus cosine delta x over delta x as delta x goes to 0. And that one we know. What's that one?
Other side you go.
What other side? Oh, I factored it out. See, I took a sine x out of each of those two terms. right? So that leaves me with a cosine x from the first term and a 1 from the second term. Okay? Okay, was that really necessary though? No, it's not. In the future, if we ever see this one turned around backwards, it doesn't matter. It's going to 0 anyway, right? So the limit of 1 minus cosine theta over theta, as theta goes to 0, is 0, but so is the limit of cosine theta minus 1 over theta. You don't really have to make that switcheroo, right? We could have just said, in other words, we could have just said right there, that goes to 0, right? Just like we could say, we did this once before. Remember we had the limit of theta over sine theta as theta goes to 0? It's 1, right? Because the reciprocal of 1 is 1. So I could flip those around, numerator and denominator, and still that works, right? I don't have to show that work. That's unnecessary. See what I'm getting at? I mean, you can, but I don't think it's necessary. So what are we left with then? This term goes to 0. All we're left with is cosine x times 1. So we got a new rule.
Wait, isn't it also sine?
But the sine is multiplied by 1, right? So this whole term, because that limit goes to 0, this first term goes to 0 with it.
But I thought the sine x was outside, wasn't it?
Well, it doesn't matter. Even if it's outside, it's still sine x times 0, right? Which is 0. Yeah, and so what we get out of this then is the new rule. The derivative with respect to x of sine x is what? Cosine x. Okay? I'll give you another one for free. How about we won't even prove it. So now we're going to have 3. We're going to have 3 rules that we can now use. We've got the power rule.
Woohoo.
Okay, that's a biggie. We've got the derivative of sine. And what do you suppose the derivative of cosine x is? Almost.
Sine x minus 1.
It's negative sine x. Okay? And the reason it's negative sine x is, I'm not going to prove it, but it has to do with the fact that there's a minus sign in this expansion.
Oh.
And so you can kind of see what's going to happen. This term is going to go to 0 and this term is not, right?
Yeah.
Okay. Yep. So those are our rules.
Wait, those are also rules. Yeah. And the last one is just.
Okay.
So it's 1 minus cosine.
It's just negative. What do you mean? The derivative of cosine x is just negative sine x.
Oh no, I was just talking.
Okay. I don't think there's anything else I really need to do here.
Aside from the limit, it's x minus 0 is 1 minus
He almost was not really
cosine x over x is 0, right?
Say it again.
What?
Yeah, that's the other one. Yeah, you're right. Okay, questions? When are we out of here? 5 minutes, okay. That's a rare time when we're done early. I just can't believe it.
Should we play trivia?
Yeah, as soon as I take roll, you bet.
You did not?
You're better.